I wanted to start off this business about eigenvalues and eigenvectors by showing you how you can solve a differential or system of differential equations with it. For example, suppose I'm given the following system of differential equations. 1, 2, 3, 2. Now, let me translate it to English before I actually go ahead and do the problem. We're going to solve this system of equations. So let me remind you how this looks. This means that dx over dt equals x plus 2y, and dy over dt equals 3x plus 2y. Both x and y are functions of the variable t. So if you were to go and subtract the one side off, you see that the variables are all on one side and the other side is 0. So we're going to first work on homogeneous systems of equations. That's where one side is equal to 0 like that. Now you may, if you look at this version of it, let me grab these two equations here. And I have x plus 2y, and I'm going to write that equals x prime. On the other hand, I'll have 3x plus 2y will equal y prime. Now typically to solve something like this, you might try to eliminate x or y. So for example, I may try to subtract the second equation from the first, and I'll get negative 2x, so the y's go away, and that equals x prime minus y prime. This is a problem. We've never had a question before. We've never dealt with a thing before where you have two different derivatives of different functions equal to this. We don't have any kind of formulas to deal with this kind of stuff. So what the problem is the fact that we're stuck. If we try to get one of these alone, you're still going to have a mixture of x and y, although you'll have the derivatives. So what happens here I'm not going to be able to go and try to get x by itself because of stuff like this. If I tried to go and wipe out the x's, I'll get a similar kind of an equation, but y will be solved on one side. So this method doesn't yield very much help. This is not like an ordinary system of equations where these things would be numbers. Then you could do this stuff and get x and y alone because you're able to combine the numbers. The derivatives of functions, not so much. So, let me explain what you do. When you have x and y in both equations, we say that the equations are coupled. And our task is to try to decouple them. That's the gist of what we're going to be doing, is somehow breaking these apart from each other. Right now they both have a mixture of x and y. What I want to do is get a system of equations where I just have x alone and equals just derivatives involving x, and then only y's alone and get just derivatives involving only y's. And that's what this procedure will do. So the first thing we do, let me rewrite the equations in matrix form. It'll be more useful for us this way. Like so. What we're going to do first is compute the eigenvalues What that means is the following. Lambda is an eigenvalue of the matrix A if A times sum of vector x equals lambda x, and this is for some non-zero vector x. Then lambda is the eigenvalue, as I said. X will be called the eigenvector. Now, in this equation that I have, ax arrow equals lambda x arrow, we can subtract off the lambda x. And we'll end up with the zero vector. Now, furthermore, I can kind of distribute the vector x away by doing the following. I'm leaving a little space there. But A is a matrix and lambda is just a number, so this is incompatible for subtraction unless I put an I here. I is the identity matrix. So in our case, the problem that we're working right now, matrices have 2 rows and 2 columns. So in this case, I will equal the matrix with 1s on the diagonals. So we want this to be equal to the zero vector. That means we want each and every component of this here on the left will be a vector, and each of the components will want to equal 0. Well, one of the ways we start looking at that is to take a look at the determinant of A minus lambda I and set it equal to the number 0. Well, what happens then is if A, B, C, D is the matrix A, and we subtract off lambda times the identity matrix, then when you multiply lambda through, we multiply it to each component of the matrix. That will give me A, B, C, D minus lambda, 0, 0, lambda. Notice I've multiplied the lambda through. And now when you do subtraction of matrices, you do a component by component or entry by entry. And this becomes the determinant of A minus lambda, B, C, D minus lambda. So this is what we're going to work on. We're going to set this equal to 0. And we're going to figure out what this number lambda is. So let's come back to our example. We have x arrow prime is equal to 1, 2, 3, 2 times x arrow. Remember, x arrow is probably something like this. It's a function of x, and it's a function of y. We'll typically drop the t and just write it as xy. So what we'll first do is determine the eigenvalues. And what you do for that is you look at the matrix minus lambda times I. Now this is a 2 by 2 matrix, so the way you figure out this determinant is you multiply by this diagonal that goes from top left to bottom right. And then you subtract the other way. Let me go ahead and multiply this stuff out. So I have 2 minus 3 lambda plus lambda squared minus 6 equals 0. And let me simplify a little bit here. Lambda squared minus 3 lambda minus 4 equals 0. And I can factor this. Lambda plus 1 times lambda minus 4 equals 0. So we have lambda equals negative 1, lambda equals 4 are the eigenvalues. Now, once we have those, we set out to determine the eigenvectors. When we compute the eigenvectors, this is how we do it. We start with lambda equals negative 1, and then we consider our matrix, which was 1 minus lambda. Well, the original matrix wasn't, but the one where we found the eigenvalues took that form. And I'm going to replace lambda with negative 1. So I'll get 1 minus negative 1, 2, 3, 2 minus negative 1. And that will equal 2, 2, then 3, 3. Now, note this. If we are looking at something like a minus lambda I, and that times x, is equal to the 0 vector, one of the ways it can happen is if this determinant is equal to 0. So with that in mind, that's how we found the lambdas in the first place. But then another way of looking at this, if you look at this here, this is what we have. I'm going to replace a minus lambda I is equal to this stuff. I have 2, 2, 3, 3, x bar equals 0 bar, or arrow. If you were to break this back into equations, we would have 2x plus 2y equals 0, and we'd have 3x plus 3y equals 0. Well, you could easily divide the first equation by 2, so I could take the first one, divide it by 2, take the second one and divide it by 3, and what happens then is I get x plus y equals 0, and the other one, I also get x plus y equals 0. Well, then if you subtract one from the other, you get x plus y equals 0. What happens here? These are exactly the same line, both of these equations, if x and y were numbers, that is. More to the point, these are what they call dependent equations. So I'm not able to get an explicit solution because I'm able to zero out an entire equation. So I have one equation with two unknown functions. That means I'm going to have an infinite number of solutions, not just one. So let me go and write a little bit more here. X will equal negative y. So some solutions. Well, you would have, now the 0 vector, like when x and y are both 0 functions, doesn't do anything for anybody. 0 is often an answer to problems anyways. Doesn't do anything for finding, we want non-zero solutions generally. So right here when I look at this, look at some solutions. X equals 1. If x is equal to 1, y would equal negative 1. Another pair of solutions, say x equals negative 1, well then y would equal 1. If x equals 100, y equals negative 100. All of these are possible solutions here. It goes on and on forever. What we're looking for is a representative of all of these solutions. No matter what happens, the y value is simply the negative of x. So I can use 1, negative 1 as an eigenvector. In fact, if I multiply that eigenvector by 100, I get this solution here. Any multiple will work. Well, any non-zero multiple will work. Generally speaking, if you choose 1, 1 is about as easy as it gets unless you have 0 available. And like I said, you cannot use a 0 vector. So I will use 1, 1 as my eigenvector for this case. This is for lambda 1. So when lambda equals negative 1, the vector 1 comma negative 1 is the corresponding eigenvector. Now move on to the other eigenvalue. A second eigenvalue that we found was lambda equals 4. So now when I go and look at the matrix, 1 minus lambda, 2, 3, 2 minus lambda, with this being the case now, I will get negative 3, 2, 3, negative 2. Now if you remember, we're trying to take a look at things that solve this system here. So this would break down as the following. We would have, as an augmented matrix, we might write it in the following way. Or negative 3x plus 2y equals 0. 3x minus 2y equals 0. Once again, if you add these two things together or subtract them or whatever you want to do, most likely add them together, you will get 0 equals 0. Let me pause for a moment. I made a mistake right here. You won't get x plus y equals 0. You'll get 0 equals 0. So you can use either one of these equations, or it's just one equation to get this. In this case, it's a little bit different. They're not identical equations, so I can use either one of these for my answer. So let's start with 3x minus 2y equals 0. The best we can do is solve for x in terms of y. So I get 3x equals 2y. And I want to get y in terms of x, so I'm going to divide by 2. I'll get 3 halves x equals y. And now I want to invent an eigenvector that is as easy as possible, and avoiding fractions would be nice. So I can choose for my eigenvector any multiple that I want. I think that it's going to be easiest when x is equal to 2. When x equals 2, plug it in, the 2's will cancel. You'll be forced to have y equals 3. So remember, this is not unique. You can find any multiple of this will be allowable. So when lambda equals 4, we have 2, 3 is the corresponding eigenvector. So we have our eigenvalues and we have our eigenvectors. What is the big deal? This is the big deal. This is a result from linear algebra. It is a fact that you can take the matrix that you have given, like this, and rewrite it in the following format. So what we have here is called the diagonalization of this matrix. Notice what we have here. You can see in the matrices that we have, the first matrix has its columns are the eigenvectors. Now go to the next matrix. Its columns are the eigenvalues. They show right here, -1 was an eigenvalue and 4 was an eigenvalue. Whatever eigenvalue you choose first, its eigenvector has to come first in this matrix over here on the left. And then 4 was the second eigenvalue found, and of course the second eigenvector is there. Now here's where it gets very cool. We were trying to solve the following. X arrow prime was supposed to equal 1, 2, 3, 2, X arrow. What I'm going to do is replace this matrix with all of this stuff. Now up here, you can see this little thing here is the inverse of this matrix here. We don't actually have to know how to solve for an inverse to use this method, but I do have to know they exist. One of the things I can do to take this matrix out of here is to multiply the left by its inverse. And so I will get 1, -1, 2, 3 inverse times x bar prime. This is equal to what's left over here on the right is -1, 0, 0, 4 times 1, 2, 3, 2 inverse x arrow. Now what you'll notice here is on the left I'm going to have still a derivative vector but times the inverse, and I have the same exact thing over here. I have the same inverse matrix but times the vector itself. So what we'll do now is let y arrow equal 1, 2, -1, 3 inverse x arrow. Then since this is this matrix in front of here, if you will think of it just as coefficients, this whole thing then, this whole left side can be rewritten as y arrow prime equals -1, 0, 0, 4 times y arrow, sorry. This will be the derivative of, say, a w, and then the second component may be a z. But look how easy the right-hand side becomes. If I'm switching to w and z's because I don't know for sure, this is simply dw over dt equals -w, dz over dt equals 4z. But look how simple they are to solve now. On this, I can write dw over w equals -t, and then when you solve this, you'll get ln of the absolute value of w equals that wasn't right. That was -dt. So this will equal -t. If you exponentiate, you'll get the absolute value of w. And I don't need to write my constants at the end of this because what I'm really searching for are just the solutions y1 and y2. We already know what the general makeup of the solutions will be. But I will get a constant when I break out of the absolute value because I want the constant to allow for there to be plus or minus numbers. Same thing goes with the second one. I will get dz over z equals 4 dt, or z will end up equaling c2 e to the 4t. So then this is my y vector. It equals c1 e to the -t, c2 e to the 4t. Now if I want to go back to x, that is substitute my way back, remember that y was equal to Let me see. Let me go back and see what it was. 1, 2, negative 1, 3. Inverse times x. So if I want to figure out what x is, I'll multiply both sides by this matrix, and I'll have 1, 2, negative 1, 3 times y arrow will equal x arrow. And now I'll go ahead and plug in my numbers, or what I have for my y, which is this stuff here. I'll get 1, 2, negative 1, 3 times c1 e to the negative t, c2 e to the 4t. And this is the solution to the differential equation, system of differential equations. Let me actually multiply this through. Something you should remember from your days of doing matrices is that this is a 2 by 2 matrix, 2 rows, 2 columns, and this is what they call a 2 by 1 matrix, 2 rows and 1 column. When I multiply them together, I will get 2 rows and 1 column. So let me go ahead and actually do that. If you remember, the way you do this multiplication is I take this one and multiply it by c1 e to the negative t. And then I take this 2 and multiply it by c2 e to the 4t. And the same thing goes when I go to the next row. I repeat the idea down here. I'll have negative 1 times c1 e to the negative t plus 3 times c2 e to the 4t. And don't forget this is equal to x with an arrow. Now I can break this up into 2 vectors. I'm going to drop the 1 and negative 1 and just put what's left there. c1 e to the negative t. And at the bottom I'll have negative c1 e to the negative t plus 2 c1 e to the 4t, that's a c2, 3 c2 e to the 4t, and you can even go a little bit further than this. I'm going to strip out the c1, and I'm going to strip out the e to the negative t. Same thing for the next one. I'm going to strip out the c2, and I'll get 2, 3 left over, e to the 4t. And these are my solutions to the differential equation. If you really want to know what these are, you'll have x of t, that's the first component, will be the first row. That'll equal c1 e to the negative t plus 2c2 e to the 4t, and y of t will equal negative c1 e to the negative t plus 3c2 e to the 4t. And you see they take the format of our homogeneous type of equation solutions that we've had before. So it does match those, but this you are permitted to write your answers in vector format, which is here. And I want you to see the features of the answer. What are the features of the answer? First of all, it was 2 derivatives. You had a dx, or x prime, and a y prime. So as not surprisingly, you get 2 constants as a result of this process. But more importantly, when you're looking at the answer, I have my constant as per usual. Let me make this pretty plain so that it's easy to see. And now I have it. Take a look now. This negative 1, 1 is an eigenvector. This 2, 3 is also an eigenvector. We found those by playing around with the matrix. But not only that, look at this negative 1 up here. That's an eigenvalue. And that 4 that's there, that's also an eigenvalue. So the idea is this. If you're given one of these systems, you just find the eigenvalues and the eigenvectors, and you can immediately write the answer. So, when solving, at least for 2 by 2 matrices, compute the eigenvalues. Let's say they're called lambda 1 and lambda 2. And their corresponding eigenvectors So if you find these two things and the two eigenvectors, the answer is x arrow equals c1 k1 arrow e to the lambda 1 of t plus c2 k2 arrow e to the lambda 2 of t. And so if you just find these things based on what I showed you earlier, the real trick that these things do is they give you an opportunity to solve a system of equations that are now decoupled. Notice that x is alone, or w in this case, and the other variable is alone. The variables are now decoupled. I thought it would be important for you to see why this works, because most textbooks just explain how you go about getting the answer and not why it actually works. So I wanted to make that clear. All right, let me do an example. Example 1. Let's say we want to solve the following system. We have 1, 6, 5, 2, x arrow. So our game plan is to figure out the eigenvalues and the eigenvectors. Once we do that, we'll be able to have a solution to this thing. So for the most part, you compute these without actually doing anything else. I'll show you. Let's start with the eigenvalues. For these things, we want the determinant of a minus lambda I, or 1 minus lambda, 6, 5, 2 minus lambda, with that determinant equal to 0. Let me go ahead and multiply through 1 minus lambda times 2 minus lambda, minus this way, minus 30 equals 0. Let me go ahead and multiply out 2 minus 3 lambda plus lambda squared minus 30 equals 0, or lambda squared minus 3 lambda minus 28 equals 0. This does factor. I get lambda. I think I want minus 7 times lambda plus 4 equals 0. So immediately, I know that my answer looks like this. C1 K1 arrow times e to the 7t, because one of my lambdas was 7, the other one was negative 4, and the other answer so you can see the eigenvalues up here in the exponent. Now I just have to figure out what the eigenvectors k1 and k2 are. So now the eigenvectors. Okay, I'll start with lambda equals 7. So then when we start to look at, basically it's an augmented matrix. Where's my original matrix? 1, 6, 5, 2. I'll put 1 minus 7, 6, 5, 2 minus 7. And let's see what happens. Here, I'll get negative 6, 6, 5, negative 5. Now recall that this is equivalent to the equations and you can divide the first equation by 6 to get negative x plus y equals 0. You can divide the second equation by 5 to get x minus y equals 0. If you add these things together, they wipe each other out. So only one of these equations is useful to us. I think for myself, the second equation, well, they're equivalent, but I will use the second equation. I'll get x minus y equals 0, which is the same as x equals y. Now, when you're creating your eigenvector, you may use absolutely any number you want for x or any number you want for y. If I choose to use 1 for x, then y will be forced to equal 1 as well. And so this is one of my eigenvectors. Note, you could make this anything. This could be 100 and 100. It's just, that's the reason why it can really be anything, is because the c's out here can suck in anything that it needs to or give away anything they need to. So that one was easy. Now let's go to the other one. The other one was lambda equals 4. So this time I have 1 minus 4, 6, 5, 2 minus 4. So when I work this, I'll get negative 3, 6, 5, negative 2. Sorry, lambda equals negative 4. Plus, plus. That means that'll make this a 5, 6, and a 5, 6, as I expected. We can immediately go to 5x plus 6y equals 0. You can ignore the other one. You're only going to get one equation out of these things. There'll definitely be a dependent system no matter what. So let me go ahead then and get y in terms of x. What I typically do is I'll write 5x equals negative 6y, and then I'll divide by negative 6, so I'll get negative 5 6th x equals y. Now, while it's not required to pick easy vectors, I'm going to pick easy vectors. I am going to let x equal 6. If x is equal to 6, then y will be negative 5. Remember, any multiple of this vector is quite allowable. So my second eigenvector that I may use is 6, negative 5. And voila, my solution. Here's the answer. You will get C1, K1 was our first eigenvector, and it was 1, 1. Our first eigenvalue was 7. Then we have C2, my second eigenvector, and then e to the negative 4t. That shows my second eigenvalue. And there is the solution to a system of differential equations. Now, a couple of notes. For n by n matrices, you'll have n constants. And you'll probably have n different eigenvalues, although that does not have to happen. You could possibly have n different eigenvectors, although that doesn't possibly have to happen either. So just keep in mind, just like when we have higher order differential equations, we get more constants. What we'll do in the next video is we're going to start to examine different types of eigenvalues. Say we have repeated eigenvalues. Say we have non-real complex eigenvalues. they'll lead to results that are similar to what we've had throughout the semesters in single equations.